So today I'm going to repeat a talk that I gave for the. I'm Craig Kaplan, by the way, for those who don't know. That I gave to the forum, or Astronomy 101, which is a series of presentations that we give for people who are beginning their careers in astronomy, as I am. So I'm a retired physician, and when I was first giving talks to students in my instructor career, I had a faculty advisor, and I went to him and said, I feel like a fraud in front of these students. I barely know enough to talk to them. And he said, your job isn't to be an expert, it's just to stay one step ahead of your audience. So that was easy with first and second year medical students, not so easy with this audience, but I'll do my best. So what I've learned to do is, because I like doing this, is how I learn, is making these talks and then sharing them, is I've gotten really good at admitting when I just have no idea beyond what's on the slide or understanding why. So people who are good with that in the room will appeal to them. So this talk is going to be about the sun. It's going to follow the path of a photon as it's created in the core of the sun, and imagery becomes a photon that excites an aurora in the Earth. We're going to just follow everything that occurs along that pathway from the core of the sun into the Earth's atmosphere as it becomes an aurora. And we'll stop along the way with various things to explain that. So in particular, what I'm going to address is the general characteristics of the sun, the structure, layers, and zones of the sun, surface features, its magnetic field, sunspots and solar cycles, flares, CMEs, and counter-rotating interacting regions, which will define all of these, the solar wind, and finally the effects of all these things on Earth that we experience ourselves. The sun is about 4.5 billion years old. It'll end its life cycle in about 6.5 billion years. So it's a little less than halfway through its life cycle, and it's destined to become a white dwarf star. And I learned during my talk on the life and death of stars that that's because it doesn't have enough mass to become a type 2 supernova, and there's no companion star from which you can draw mass to become a type 1a supernova. So it's destined just to become a white dwarf and eventually fade away into a black dwarf. And that will be our sun's future. It produces about roughly about 10 to the 34th joules of energy in 1 year. The U.S. consumes about 10 to the 20th or 10 to the 21st joules of energy annually. So the sun produces enough energy in 1 year to fuel the U.S. energy consumption for 10 trillion years. So this just takes 1 year of fun dust for 10 trillion years. It's the equivalent of one nuclear weapon produced every second plus. The sun's composed of 92% hydrogen, about 8% helium, and a small amount of metals. And just to specify, unlike chemists in the group, astronomers think of every element beyond hydrogen and helium as a metal. So all the rest of the elements are referred to as metals in this listing. There are some that are intermediate products, but nickel, calcium, sodium, magnesium, and iron are all produced along the way. And if stars much older than the sun, with enough mass, they end their life by producing iron, which once it starts being produced, results very quickly in a type 2 supernova. Elements in the sun exist as plasma, which is the fourth state of matter from the ones that we're used to dealing with. It's an electrically charged gas, and it consists of atoms stripped of some or all of their electrons, plus the free-flowing electrons, and it's created when additional energy is added to a gas, including heating at the high temperatures. It's actually the most common state of matter in the universe, and it's found on Earth in the upper atmosphere, in auroras, TV sets, and fluorescent neon lights. But ordinarily is otherwise not found ever. The sun, interestingly, is described as an average star, but ranks actually in the top 10% of stars by mass. It's a yellow star in the mid portion of its main sequence, and its spectral class is said to be G2V. It contains 99.8% of all the mass in our solar system. It's a pretty weighty object in our solar system. Compared to the Earth, it's about 3 times the mass. Volume, about a million Earths would fit into the sun's volume, and its gravity is roughly 30 times that of Earth's. Interestingly, the sun would be white if it was viewed from space. But the Earth's atmosphere scatters some of the blue-violet rays as they come through, and so we see, which is why the sky is blue. As you see those blue-white rays scattered into the sky, the remaining colors that reach our eyes cause it to appear to be a shallow, a yellowish. But if we looked at it directly from space, it would look white. It's about 93 million miles from Earth on average, because we don't have we're not at the center of a circular orbit, we're an elliptic. It's a slightly elliptical orbit. It's a little further, a little closer than that at times to its orbit, but on average it's about 93 million miles away. And that's considered to be what's called 1 astronomical unit. So if you hear things described to us, distance to Earth being an astronomical unit, it's how many times the Earth's distance from the sun it is from whatever the basis might be. So if Jupiter is X number of astronomical units from the Earth, it's how far it is in terms of multiples of 93 million miles, or 150,000 kilometers. It takes light about 8 minutes and 20 seconds to get to the Earth once it's released from the sun. But as we'll see, that light spends a lot more time in the sun than those 8 seconds. The sun also, with its solar system, revolves around the galactic center every 265 million years. So we're also in motion around the galaxy. Our galaxy is itself in motion. So it goes on and on, but there's a lot of motion. So the sun is composed of layers and zones, just like the Earth is, just like most planets are. The core is from 0 to 20% of the sun's radius. And the temperature in the core is around a little more than 15 million degrees Kelvin. And in the core, hydrogen is fused into helium. And the main way it's done in the sun, in our sun, because of its mass, is through a process known as the proton chain reaction. And so in this, I don't want to go through the whole thing because of time constraints, but in this process, 4 protons end up being turned into a helium. In the process, 2 of these actually turn into neutrons. And this whole process itself results in the release of gamma rays. So 1, 2, 3, 4, 5, 6. This is a neutrino. And so 6 gamma rays are produced in this process in addition to these neutrinos. And the gamma rays are high energy photons. And we'll see what happens to them as they exit the core in this. There's another process by which hydrogen can be fused into helium, but it requires more mass than our sun has. So this is the main process by which our sun produces helium. The radiative zone is between 20 and 70% of the sun's radius. The temperature there is about 100 million degrees at the outer edge. It carries energy via diffusion of electromagnetic radiation of photons. Photons created in the core get out into the radiative zone and bounce around in this zone for quite a while, on the order of 100,000 to a million years. So they spend quite a while in this zone trying to get out. In bouncing around, sometimes they lose their energy. So they get converted from gamma ray photons into ultraviolet, visible, and infrared light. So they exit from this zone often in more visible spectrums for us. And the photons that are exiting from this layer now were created around the time that Homo sapiens first emerged on Earth. So we're seeing those photons that were created when our species first evolved. They're finally getting out of the sun. The convective zone is the next zone. So we're talking about zone 3, right here. and that's 70 to 99% of the sun's radius. And it conveys energy rather than the photons themselves moving. So it's like a pot of boiling oatmeal. As the oatmeal heats up at the bottom and bubbles up to the top, and its energy is lost at the top, and the little bubbles slide down. We'll see more pictures of how that works on the sun. But the heat is carried through this layer by these little bubbles of plasma in the sun, oatmeal in terms of our analogy. The final 1% of the sun's radius is called the photosphere, and that's the point at which the sun becomes opaque to light, unable to see through lower levels. So we would consider this in a sense the surface of the sun. Its temperature by now has reduced to about 5,800 degrees Kelvin, and it's this surface from which photons exit the sun. And the sunspots and granules that we're going to discuss later in the talk are in the photosphere. The chromosphere is yet another irregular layer above the photosphere where the temperature dramatically increases from 5,800 degrees Kelvin, as you saw, to 10 million degrees and higher. And it's not completely known how or why this happens, but there are some thoughts that I'll explore later on. And there is a transition region in the upper part of this where the temperature dramatically increases from 10,000 to 1,000,000 degrees Kelvin. And at these temps, hydrogen emits light that gives off a reddish color, which is how it became called chromosphere. It can be only seen during total solar eclipses or by special satellites that are made to observe those layers of the sun by blocking out the more central layers of the sun. The second image here was taken during the 2017 solar eclipse, and you can see here parts of the chromosphere. This is a graph of what happens to temperature. So you can see here that 10 to the 4th for most of it, and then this is this transition region where the temperature goes from 10 to the 4th degrees Kelvin up to 10 to the 6th degrees Kelvin in a relatively short distance, speaking in terms of sun. So that's the chromosphere, and then finally the corona is the atmosphere of the sun. It's only visualized during total solar eclipses, unlike the chromosphere, and it's much hotter than the sun's surface, as high as 3.5 degrees Kelvin, million degrees Kelvin. And it's possibly that high velocity jets called spicules that we'll see when we look at some of these other structures are what convey the energy to increase the temperature from deeper areas in the sun up to the corona. Things called prominences, which we'll discuss in a little bit, extend through the corona and may twist, which causes things like coronal mass ejections, flares, things like that. And again, we're going to talk about all that. This image is also taken during the 2017 total solar eclipse. You don't see the chromosphere except for maybe this little thin area up here, but this is the corona here. Surface features of the sun include things that I've mentioned but haven't described much yet, called prominences, solar flares, filaments, spicules, which I've mentioned also, plages, they're called, and supergranules. Sunspots we're used to seeing. I suspect there's one or more telescopes set up out front and we'll be able to take a look at some sunspots after this talk or after the talks conclude. They are relatively cool areas of the sun that appear dark only because we visualize them against a much, much brighter surface of the sun. But they're quite hot. They in general are larger than Earth. So they're about 10 to the 4th, 10 to the 5th miles in diameter. Earth is about 8,000 miles in diameter. They're magnetic phenomena, which we'll talk about in more detail when we talk about the sun's magnetic fields. They're often formed in pairs of opposite polarities, so they're like two ends of a magnet. And this is one of the reasons how they loop up and become prominences that we'll see in just a minute. The location and number of the sunspots vary with the solar cycle. So when the solar cycle is more on the average, more on the higher side, more sunspots, more activity, more complex magnetic fields, there are more sunspots, and they tend to be located away from the equator, more at the 60 degrees north and south level. We'll again see this in greater detail when we talk about magnetic phenomena. And then during the more quiescent periods, they're fewer in number and they're located around the equator. So one way that they know when the sun is beginning to approach a solar maximum or beginning to enter the solar maximum size is they see sunspots migrating, the appearance of sunspots migrating from the equator more towards the 60-degree positions, and that usually heralds the beginning of the solar maximum cycle. These spicules that I referred to earlier are thin spike or flame-like structures that originate lower than here, but end up conveying energy up into the corona, which may be one reason why the corona can become so much hotter than some of the cooler areas beneath it. This is another image of a spicule here arising into the corona, projecting some of the high temps deeper in, out into the corona, which enables it to become hotter than the chromosphere and photosphere. Granules are images of the sun. Again, imagine this to be a pot of boiling oatmeal. And they are areas where heat is conveyed upwards into the center, the more bright areas of the granule. And then as it cools off, it subsides, these darker areas going lower. So it gives off its heat to upper layers or into the photosphere, into higher layers, and then subsides down. So you can see this. Oops. So you can see them, imagine them boiling up and then going down. And these are collages. Oh, shoot. I finally got it going. So they're giving up their energy, and then the plasma is subsiding down into deeper layers. They get more energy, coming back up again. All done. Advertisements noted. Plages, which in French means beach. So it looks like little beaches, are bright areas, bright clouds in the chromosphere that tend to form around sunspots. They have higher temperature and density than the surroundings, which accounts for their bright color. And they may be another important interface for coronal heating, although I couldn't find out much more about them than that. So that's all I know, that there may be yet another, besides the spicule, another mechanism by which energy is transferred from deeper layers into the corona, allowing it to be so much hotter than more superficial layers of the sun. These are another view of plages here from Wikipedia. I should have said earlier that I tried to be clear about where I've gotten most of these. Some of like the picture of the proton process. I actually got, that's such a creative picture. I actually got permission to show that from this group because they were very clear about requesting permission. So I emailed them and they gave me permission to use it in the talk. I haven't gotten it for every image on here. In fact, that's the only image on that I've gotten specific permission on. But I've tried to get to where I've gotten it from. I have the references. So if any of you want the publications that these images come from, I can give that to you because I've got all the URLs from all of this. All right, so prominences and filaments are loops of plasma pulled up by twisted magnetic fields that we're going to discuss. They are cooler than the sun's surface, and there are quiescent, eruptive, and surge types that I won't go into detail on. But there are, whether they're called prominences or filaments, actually depends on your perspective view of them. They're the same phenomenon. So this is one seeing a loop of plasma and electromagnetic field here seen against the backdrop of space. So you see the loop and it's very, very bright against the backdrop of space. But if you see it against the backdrop of the sun, it's actually cooler than the sun, so it looks darker. So here's where they happened to capture one that was right on the edge of the sun. So this part is the same phenomenon, a loop here going up here and back there, one direction or the other. And when seen against the sun's surface, it's kind of darker because it's cooler than the sun. But when seen against the backdrop of space, it's quite bright. We'll talk about how these form and how they give rise to things that occur that affect Earth. So flares happen when the we'll talk about how this occurs. We'll talk about the mechanism, but when the loop comes up, it twists in a way that the lower parts actually touch. And when they touch, the magnetism reconnects. So the loop touches, and I've got images of how this occurs. And when they touch, it produces a flare, a bright burst of energy. And if they touch, and there's enough plasma above them, they inject that plasma out into space, and that becomes a coronal mass ejection. And this is called reconnection. Each one releases a burst of radiation, at least, if not plasma, equivalent to 1 million hydrogen bombs. The largest of these contain enough energy to power the U.S. for 100,000 years. And again, they're caused by short circuiting, which we'll see. But you can actually see it happening in this. So this is one forming. You can see the loop coming up, and then the bottoms touch. I've got clear things that show this later on that we'll talk about. Flares can have effects on the Earth. They can cause radio blackouts, lower the satellite orbits, because as they heat the atmosphere goes up. So the satellites that are used to orbiting at a certain density of atmosphere are suddenly orbiting at a much higher density. It slows them down, lowers their orbits, and affects their function. So flares can have very significant effects on satellites, including the GPS satellites. They're often associated with CMEs, and there are classes of them that are logarithmic. So this is the watts per square meter of C, M, and X class flares. I'll show you some websites, you can look at whether any of these are in the offing or likely to affect Earth, and they're classified. And usually, like the X class flares, the ones you read about in the newspaper, they give rise to northern lights warnings or heads up for people that are in the U.S. or northern areas. Coronal mass ejections, as I mentioned earlier, it's actual solar material ejected out into space, not just energy. So it's an immense cloud of magnetized plasma. The generated light flare, magnetic reconnection, are much more powerful. And there's a cannon analogy that a lot of the references that I read with this talk here talks about. So if you imagine a cannon firing, the flare is the actual burst of white light you see when the cannon fires, which is the flare, but the cannonball is actually the coronal mass ejection, which is much more damaging, potentially, if aimed in the right direction, than we see. And I'm going to go into some of the effects that these things can have on Earth. Here you can see more about. So this is the reconnection actually occurring. This is the flare, and this is the plasma above it that will be blown out into space when the reconnection causes it to lose its magnetic connection to the sun, and then goes out into space. Here's a cartoony version of what happens in reconnection. When you look down here, you reconnect bond. So again, you reconnect, solar flare, ejection of coronal mass ejection. So that's magnetic reconnection. And here's another picture of a through-up satellite. So I'll let that loop a couple times so you can get an idea. Coronal holes are relatively dark areas in the solar corona visible in extreme UV light and X-ray solar images. They're cooler and less dense regions of the corona. They allow escape of high-speed solar wind streams, that we'll talk more about when we discuss solar wind. But then they're also involved in creating the co-rotating interacting regions that I'm going to detail earlier. These, I had never heard of these until I began the research on this talk. But they do affect the Earth, so we'll talk about those. The sun is a highly magnetic object, just like most objects in the solar system. So the sun's magnetic field, a dynamo is a machine that converts kinetic energy of motion into electricity. So the electric currents and the electric currents in turn can produce magnetic fields. So the dynamo of the sun is felt to be somewhere in the interface between the convective and radiating zone, but it's not clear. And the moving charges of the plasma, or plasma are moving electric charges, creates a magnetic field. And sunspots, prominences, and filaments, flares, and semis are all magnetic phenomena. You can see here why this area is cool. These areas of the sunspots are cooler because this is the magnetic field projecting up through the surface layers into the photosphere and corona. And this magnetic field blocks the hot rising gas from getting up here, which results in these sunspots being cooler and why they're darker than the surrounding photosphere. These magnetic loops go above here, and we'll see what happens with them. So the Earth has a magnetic field too, of course, but it's a stable magnetic field. It changes very slowly with time, but in general, it's stable from year to year, decade to decade, century to century, because it has a rocky crust. So, but the sun is more complex because it doesn't have a fixed surface. So, in the sun, the sun rotates, the surface rotates like the Earth does, but because these areas are not fixed, the equatorial regions of the sun rotate much faster than more polar regions. So one full rotation of the equatorial sun is 25 days. And you can see up here towards the poles, it's actually 35 days. So the sun's surface, there's actually differential rotation. And this differential rotation causes twisting of these magnetic fields. So these are the magnetic fields early on in the solar cycle, and these are the magnetic fields that that become more and more twisted. And I'm sorry, I forgot this in my. I'll do that as an idle prop. So.
So, question. Let's say you have an object closer to the let's say it's a sunspot. And all you can just visualizing it as a surface mark on the sun. Since that region rotates slower, would an object of sunspot greater complete that rotation in basically the same number of days that it takes.
So you may remember these from your so you may remember these from your childhood. This is a slinky. So if you imagine the magnetic field twisting, if you twist the slinky, watch what happens to the. See how it naturally curls and becomes a prominence. So the differential rotation of the sun causes the slinky, causes initially a loop, which then combines, reconnects. This bottom part falls back towards the sun, and this top part is a flare, and then it flows up towards Earth. I knew what it was because I didn't think I was going to get this time again when I gave it, and so I gave my first slinky to my grandson. He'll be happy to know that since I bought my first one at Walmart, they went from $6 to $2. So in case you want to buy some, it's fine. So that's how, so just twisting an already twisted object will cause it to do exactly what's happening up here. And all the energy for that comes from the twisting field and the differential rotation of the sun.
Is everything rotated, like from the west to east?
Yes. Yes.
Basically everything except for like Neptune.
Right. Neptune and
Uranus? That's like not as.
no, I think Venus. I think Venus has
Well, Venus goes backwards.
Yeah.
right. So Venus has
Venus
clockwise
and
direction. Correct. When viewed from the north. Right. And that's thought to be from an impact really that caused Venus to actually flip, whereas Uranus just got knocked on its side. So then again, this is another cartoony picture of the phenomenon I've been talking about. This is a film from the Goddard Space Center, Science Center. It's narrated, but you can't hear that because we're not connected to that. You want to try? Would that be quicker? Yeah. I thought the HDMI would catch the. That's okay. We're fine. All right. So anyway, these are two NASA satellites. These capturing the phenomenon of magnetic reconnection from different perspectives. So that's again explaining the phenomena where reconnection occurs and one goes out into space and one falls back. Here's a version of it. And then a little later in this, it's going to show actual visuals from these two satellites that document this. So again, a very complex magnetic field to the sun. This is showing data obtained. And this is from the different satellites showing the energy profile that documents the reconnection. What's happening to these plasma flares? Flare and coronal mass ejection. I think the rest is more verbiage then. All right, so any questions on magnetic reconnection? One of the core concepts that I encountered. All right, so there are, as I mentioned earlier, there are cycles of the sun. So there are sunspot cycles, and also there's a solar cycle that I'll explain. Galileo noted that sunspots vary in position and number. Each cycle lasts around 11 years, not exactly 11 years. Minimum to maximum or maximum to minimum. As I mentioned, during the minimums, sunspots tend to be located around the equator, and the magnetic field lines are more orderly through twists and tangles. Whereas during maximums, sunspots migrate to the mid-latitudes, and magnetic fields become increasingly twisted and tangles. And the number of CMEs and flares increases dramatically during these maximums. This is called the butterfly diagram, and it shows the number of sunspots, their intensity, and location over time. So I've taken one cycle and outlined. So this is the minimum, and you can see here on this line, just marking the minimum, how these sunspots are closer to the equator, but fewer in number. These lines indicate higher, whereas these sunspots are greater in number. Here's the number averaging. So the minimum, this is the number of sunspots that were occurring. The maximum, this is the number of sunspots that were visualized. And this repeats itself, giving it the name butterfly diagram. Each minimum and maximum, or maximum and minimum, is associated with a reversal of the north and south magnetic poles in the sun. So we're due for a reversal soon, according to the time. And it usually heralds a period of heightened magnetic activity. And it was predicted to occur we're in solar cycle 25. I'm not sure what one was. And it was predicted to occur in 2024, but I don't know that it's occurred yet. But it's also, it takes a while for them to detect this. So there's something also called the Hale cycle or solar cycle, which is one complete cycle, if you will, where the time taken for the poles to switch polarity and then switch back. So it's two of the solar suns of the sunspot cycles that we're talking about, or 22 years. And it's confusing because sometimes the sunspot cycle is referred to as a solar cycle. But I have to know which one they're talking about if you actually stick with the details. The people have thought over years that sunspots have a direct effect on Earth. The most consistently described association was the Little Ice Age, which is a period of regional cooling, particularly in North America, and it was associated with the Maunder minimum, during which time there were very few sunspots. So this is a graph of solar activity events taken from carbon-14 dating, of course, both ice cores and rocky cores taken from the Earth that they used to interpret the degree to which there was solar activity. And this is the Maunder minimum right here. But there's really no evidence for any of these associations. And there was a paper in 2017 where they identified the Maunder minimum as only one of the factors that were associated with the ice age. And the most significant factor was they think was a lot of volcanic activity during that time, which spewed large amounts of ash into the atmosphere, caused global cooling, and really caused the Little Ice Age rather than the actual sunspots themselves. So there's no conclusive evidence that they have any effects on Earth. The solar wind is a stream of charged particles that is released constantly from the corona. It's mostly electrons, protons, and alpha particles, which are helium nuclei, with trace amounts of other metals. It was first suggested by Richard Carrington, and Eugene Parker was the first author to use the term solar wind, for whom the Parker Solar Probe was named. And there's an interesting story that goes with this because Parker's initial scientific paper was rejected by two bureaus where he postulated the solar wind for the Astrophysical Journal. And for those of you who remember, this actually was in a large part in jeopardy last year, and also was part of my talk on the life and death of stars. The Chandrasekhar was the guy who came with the Chandrasekhar's limit that stars can only reach a certain size before they explode. And his paper, initial paper, arguing this limit was rejected by a paper, and their author, the paper's editor, overruled and published it anyway. So Chandrasekhar passed it forward by overruling the editors and publishing Parker's paper anyway, and it ended up becoming believed theory right now. The solar wind emanates from the sun in a radial pattern. It's called an Archimedes spiral. So an Archimedes spiral is what occurs when a spinning object emits particles which have both radial, directly away from the object, and spiral velocity or momentum. So this is an Archimedes spiral right here from a site called mathcurve.com. And you can see the little dot right here. It's moving out straight along the line, but because it also has spiral velocity, it traces out this line. And so the solar wind traces out an Archimedes spiral, radial plus spiral angular momentum. Via the solar wind, the sun's estimated to be losing 1 to 2 million tons of material every second. It's a big boy though, so it's not going to run out of material anytime soon. But these, the solar wind has both fast and slow components. The fast components, which are also hotter, emanate from these coronal holes I mentioned earlier, and nearly matches the composition of the photosphere. The slow component, no one's really sure where that comes from per se, but I happened to see a paper that, because I've been reading a lot about this stuff, Adam just gives me a lot more articles. So studying this article and in Sky Telescope, it argued that the coronal holes may also be responsible for the slow component. But it's the composition of the slow components is more consistent with the corona, whereas this is more consistent with the photosphere. But what happens is the fast component, as it's ejected, runs into the slow component and hits it, and it produces a shock. And that shock wave can produce effects on Earth. And the shock wave is referred to as a co-rotating interacting region. And you see here the fast component running into the slow component, and there's the shock wave right there. And the shock wave goes out and affect planets like the Earth, and it causes electromagnetic effects on Earth, like coronal mass effects. Nowhere near as severe, but like that. So we're reaching the Earth by the space weather.
Wait, can you repeat that part again? So it creates a shock wave, and then the shock wave, what?
Yeah, so here's the sun, and as the shock wave occurs, it continues to expand out into space, eventually reaching the Earth.
What effect does it have on?
Affects some of the coronal mass ejections. It affects electrical transmission, magnetic lines, yeah, those things. Right, and may cause aurora.
They're most likely because
Yes,
it'll get through the next.
correct. Thanks for stopping and explaining that. All right, so quick review here as we discuss effects on near to Earth space. So flares are energy released from magnetic loops and reconnection. It's the muzzle flash of the cannon. CMEs are matter released from magnetic loops and reconnection, the cannonball. And CIRs are compressed areas of solar wind that can produce shockwave effects on Earth. Flares have relatively minimal effects on the Earth's surface because the Earth's magnetic field protects them from the purely energetic magnetic effects of them. However, the Earth's atmosphere, as I mentioned earlier, can be affected by the high energy photons, including X-rays of a flare. The Earth's atmosphere heats, expands, and degrades satellite orbits, including GPS, and can cause direct damage to satellites that are in high orbits from highly energetic radiation. The radiation induces magnetic field from the satellite and causes direct damage.
It's a long way for you blackouts to
Yes.
that bounces off the atmosphere. It works out.
Yeah. Coronal mass ejections and to a lesser extent CIRS, co-rotating interactive regions, can cause atmospheric effects on the Earth's surface from events that occur on the sun. And that's the definition of a geomagnetic storm. They're caused by these, and they have a scale of G1 to G5. you can read that, but I'm going to describe some of these events on Earth. So the Carrington event, remember the name Carrington, was the first person to propose the term solar wind. This is a report of that. Was a solar flare directly observed by Richard Carrington. It caused extremely bright auroras, atypically south. People in the Caribbean were able to read newspapers at night because of these auroras. And gold miners in California awoke and made breakfast because they actually thought it was sun. It caused fires at telegraph stations and telegraph poles, and telegraph operators were able to operate their equipment without connecting to batteries because of current that traveled through the telegraph wires into their machines. Railroad ties were ignited by current in the railroad rails, the iron railroad rails. So this is a fairly significant event, which in 1859, we didn't live in the same world we live in right now. Imagine this happening right now. I'm going to show you an article about the potential for that later on. So other such events, in 1921, there was a New York railroad storm, which caused worldwide destruction of telegraph and telephone systems, and it caused fires at telegraph offices in New York City. There was a 1940 superstorm that was caused by a pair of Iraqi CMEs. It disrupted power grids and long-distance communication across North America. Others, I won't go into detail because we're running short of time. But
how long they last? Those storms last?
Well, on the order of days. They're not days. Yeah. So in this storm in '72 forced AT&T to redesign its system of transatlantic cable schedules so disruptive for them. The Quebec blackout caused an energy surge that overwhelmed Quebec's electric grid and caused a province-wide blackout. And NASA has a system for tracking Earth orbiting objects, and it lost track of 11,000 of the 19,000 objects it was tracking because all the orbits were lowered and changed by this event. So they also changed their system as a result. They followed AT&T's. So this is an article written in 2024 that says we're overdue a once-a-century solar storm. If the Carrington event struck today, it would be catastrophic. The potential effect could be on the order of $1 to $2.5 trillion in damage. It would cause a complete interruption of the air traffic control system. I ate lunch actually with a woman who used to be an air traffic controller at Rochester in Baltimore, and I actually asked her about this, and she said that like the 5-minute blackout that occurred in Newark, where the air traffic controllers lost track of all the airplanes for 5 minutes, it causes enough stress that some air traffic controllers are known to have heart attacks when these sorts of things happen. And she said that the 5 minutes that this occurred in Newark must have been like a lifetime to the air traffic controllers because all you know is where the planes used to be and where they were heading from notes you were making at the time. But that's the reason they take these notes. The air traffic control systems operate on Windows XP computers. Yeah, that's how far behind we are. Yeah. So it would interrupt mobile phone networks, satellite malfunction, and it would take us months to years to recover. And it's one reason why NASA puts so much into early warning detection of things. Because you can't protect some of this equipment from damage if you know soon enough and it occurs. That's why some of these satellites are there just to participate in NASA's early warning system.
Have like about 45 minutes or something, like, I know, like.
Or flare.
Yeah, like,
Yeah.
like.
But the CMEs take 3 to 3 days to reach zero. But the flares are traveling at the speed of light.
Right.
So they take 8 minutes. Speed of light, yeah. So now we get to see the beautiful. We talked about some of the damage. Now we get to see the aesthetic value of some of this thing. So auroras are caused by charged particles from the sun interacting with the Earth's magnetic field. They're particles that are diverted. which you can actually, this is mine, I should know how to use it by now. So they deflect and come down through the poles, and they actually, the ones that pass by actually can be deflected back by the Earth's magnetic field. But they're polar events, which is why they tend to be more accented in the high north and high south. And these particles energize elements in the atmosphere, which then release. So the atmosphere, nitrogen and oxygen predominantly absorb these photons. Their electrons move up to higher energy fields and then move back down to emit photons of their own. But these are color photons rather than the high energy photons. And I'll show you some of that. They're mainly at the upper latitudes because of the sea, but we are actually, I kidded my daughter about this when I visited her in Sweden, because they are much further north than us in where she lives, and Stockholm. Please don't tell my daughter. And but we see them otherwise much more commonly here than they do there because it's where the magnetic North Pole is, not the geographic North Pole that tells where these are. So this is where, so this to orient you, so this is the magnetic North Pole, and you can see how these protrude much further down into North America than they do into Europe. The colors are caused by the specific element and the height at which these interactions occur. So red is produced by atomic oxygen at these levels. Green is produced by oxygen at these levels. Violet and blue. This is a nice graphic from NPR actually that shows where these occur. And green is often more visible, not only because it's common, but also because our eyes are much more sensitive to green than red. Probably people guess this is because in our ancient days, when we were out in the open and being pursued by a predator, we were much safer in the forest. So our eyes would never recognize green, so we'd be jumping on towards green quicker than anyway. That's why frogs always will jump towards blue, because they're jumping towards water. We're running away from the open areas into the red. Anyway, into the green area. Yeah, and it's easiest to see. So to be visible to the naked eye, this red color has to be 10 times more intense than the corresponding green color. And then this is the lower levels of platinum blue are caused by ionized molecular nitrogen. Predicting auroras, we all heard of the KP index, which is the Kensington Planetarisch. And it loosely translates from the German as planetary index number. It's global magnetic activity, geomagnetic activity, that's based on 3-hour measurements from 8 ground-based magnetometers around the world, one of which is in Sweden, not far from north of where my daughter lives, which, to remind myself, is Stockholm. It ranges from 0 to 9, and any KP index greater than 5 is a geomagnetic, classified as a geomagnetic storm. There's also something called a BZ value, which is B is any symbol. B is the symbol used to represent magnetic fields, and the solar wind fields are represented by 3 vectors in all the cardinal orientations. So the BZ is the vector that's oriented north-south relative to Earth. And when it's positive, the charged particles are flowing north to south. When it's negative, they're flowing south to north. So in the northern hemisphere, when the particles are flowing south to north, they're hitting our atmosphere at much higher energy than it would be if they were oriented in the same direction. So if you want to add information to what the KP index gives you, look at the BZ value. And if it's strongly negative, it makes auroras even more likely for any given KP value. So these are two really good websites that I check almost every morning because they got such good information. I'm going to see if we can get to them. Yeah, so this is Space Weather Live. And you see they provide the KP. Oh, where do I move it? Just drag it over. Drag it right. Okay. So this is Space Weather Live. It gives a KP index. It gives where the auroral oval is. Oh, I'm sorry. Thank you. Better? Can everybody see?
Yeah.
All right, so I've got these bookmarked in my browser, and
Oh, shoot. We did this together.
all right, so where the auroral oval is, it gives you the real-time solar wind. Down here, it gives you the BZ index. So the BZ index is oriented south right now. And these changes all change with
So is
time.
that south to north or north to south?
It's oriented towards south and north. Yeah. And then you can get a lot more detail just by clicking on these headers. So this is solar activity. Those will give you a view of where the sunspots are and where they're named. This isn't real time, but it's close. So if you go outside and look at the sun, you're probably going to see this view today. These are the solar, so these are the coronal holes that are existing right now. So these are coronal mass ejections that are pending. Sunspot regions with their names. There's a flare. This is one of those rabbit hole websites you can spend an afternoon. All right, this is a similar one that's a government website. And these give you space weather conditions. So the observed maximums, similar information. There's the auroral ovals, the coronal holes, what's going on in the sun right now. So these are the two. I discovered the first one when I was here with Bob McGovern one time, and he was looking at sunspots and trying to figure out what the numbers were. He goes, I got to go to spaceweather.com. That's how we figured it out. Yeah, yeah. So I'm going to move this off again. Well, all right, so this is Steve. Someone was talking about Steve earlier this morning. It's another manifestation similar to the aurora. It's called strong thermal emission velocity enhancement. And if that's difficult for you to remember, the reason is the name Steve did not emerge from, is not an acronym for something that's a scientific name. The scientific name was chosen to make up Steve. And so they designed it. And the reason why is that in 2016, this phenomenon was reported by citizen scientists in Canada. And there's an animated film that some of you may have seen, I've since watched it, called Over the Hedge. And in the film, a bunch of animals in the woods encounter this hedge. And behind the hedge is a totally mysterious area. But when they began hibernating, the hedge didn't exist. When they woke up from hibernation, the hedge did. So it was an ununderstandable, scary object, and they named the hedge Steve in order to demystify it a little bit. So they just named the hedge Steve. So these scientists decided to call this myth, not understood phenomenon, Steve, in honor of that film. So this was taken from Parrish about a year ago, maybe 2 years ago, and we may have to. Can you see that? Yes, that's right there. And so there was a huge amount of argument among us who were there about whether it was Steve or an airplane contract. And then the argument stopped when it did this. It switched to being upright. So at that point, we decided it's probably Steve because it'd be a very unusual maneuver for an airliner that wasn't a fighter pilot to be able to do that. So we decided that we had seen an example of Steve, and there's the movie called Over the Hedge. There's something also called structured continuum emissions, which I It's a fairly recently reported thing, but this is an aurora, and this whitish area is called the structured beam emission. It's thought to be superheated gas caused by the aurora phenomenon, but it's not. There's not much known about it. So this is the aurora that I took in October, last October. But the real pro, who's not here right now, is Joel T. Perry. He took this picture, and just for full credit. And he's the second person who got to show a graphic with this Joe very kindly. And that's finally it for me. Thank you guys for your attention.
I remember the time we were watching it, we were both there. And so, one of the nebulous just turned really, really bright all of a sudden.
Well, there's like two areas.
You can see some other stuff like over that. Go back to the regular non-inverted image. There's one a little higher. That one was getting the clarity.
That's really
Doing exciting things.
It's right now.
It's like,
Interesting. Very cool.
Tell me
Thank
if
you for
I
listening.
get that. This part of our kids, pay $2 they come up with a treat.
yeah.
Oh, you realize that you heard.
Yeah, oh yeah, they go to white thing, golden strip.
Thanks.
How many stores? And they're carrying on
Yeah.
this way. Nice. Anyway, I mean, it's like